Hello everybody, welcome to this WEkEO training on ice monitoring. I'm Alexandre Morin from Noveltis and I will be your trainer for this Jupyter notebook exercise. So the topic I've chosen for you today is iceberg tracking in Antarctica. So, iceberg calving is a process in which large icebergs detach from the edges of the ice shelves or glaciers, depending on where you're located. So this occurs naturally, but recently it gained increasing attention because this phenomenon may have links with global warming. For instance, warmer ocean waters can shift the wind and current patterns and weaken the structural integrity of the ice shelves, which should make iceberg calving more intense and more frequent. And this can also have impacts, at least in the short term, first on the local ocean circulation, on the freshwater input, and of course on the biological activity. And over a longer term, longer time scales, this calving may also contribute to the silver ice, and because it would reflect the instability of grounded ice. So this is why it is crucial to understand how and when calving occurs, and thus it is essential to monitor polar regions. And to do this, we can count on the progress of the satellite technologies and remote sensing technologies, because recently, iceberg tracking has become more accessible and reliable. So, for instance, on the WEkEO website, we have access to a lot of satellite images datasets, such as the synthetic aperture radar imagery from Sentinel-1. And also we have sea ice drift fields and other data such as ocean current models or surface wind reanalysis, which can help find drivers for iceberg trajectories. And as I've just said, wind and currents are environmental factors that can influence the iceberg drift. And but of course there are also factors such as bathymetry or the inertia of the iceberg itself. And so in this notebook we're going to investigate some of these factors, and by analyzing the trajectory of a particular iceberg, which will be iceberg A76, which is one of the largest that detached itself from the Antarctic in recent years. So it detached itself from the ice shelf in May 2021, and so due to its size and to its recent calving, it offers a very ideal case study for examining iceberg motion and examining the local environmental factors that may influence its trajectory. So we're working with a Jupyter notebook. So here I will do a little section about the Python environment that we will be using. So first of all, here's an overview of the libraries that will be necessary for this notebook. So if you're already familiar with Python, you probably already know the NumPy library, which is very commonly used and fundamental for computing ND arrays. Xarray is also fundamental when you're working with scientific data in a netcdf format. So we'll be using this library to process the different different scientific files that we want, especially current and wind data. Matplotlib and Cartopy are used to draw the different maps and graphs that we will generate during this training. Rasterio is used for reading and writing raster data. So this will be particularly useful for the satellite imagery that we're going to use. And finally, PyProj is a library that manages geospatial computation and projections and geodetic distance calculations. So you will see that we will be using that to compute distance while taking into account, for example, the curve of the Earth. So this will be used at the end of this notebook. And finally, we'll also use the EarthKit library. So this is a library that is well used with the WEkEO platform, which allows us to access data without having to download it. So all those libraries are already available in the WEkEO Lab kernel that is pre-installed on the WEkEO Jupyter Hub. But this library is not available on it, so you can follow these steps to quickly install it during your session. So you'll just have to open a terminal, which should work, yes. Activate the WEkEO Lab environment using Conda, and then install EarthKit. So I've already done it, so I'm not going to do it again, but you can just copy and paste those two commands once you've opened the terminal. And then finally, come back to the notebook, restart the kernel by clicking on this icon, and you'll be good to go with the EarthKit library. So in this cell, we import all the libraries that I've mentioned, including EarthKit. And in this final cell, so you will see for EarthKit that there is a dedicated article explaining to you all the steps required to use EarthKit. This is one of them, just setting up a cache directory. The access data will be cached here in order to ease the access if you want to use the same dataset during your session. This is a small iterator function used to normalize vectors, so this will be used later in the notebook. I'm just setting it up now. Next is a little section about the products that we're going to use. So we are going to use several data sources, satellite imagery, gridded currents and wind observation, and also iceberg tracking data. So for satellite imagery, we're going to use Sentinel-1 synthetic aperture radar images. So as our iceberg is very large, we are using the extra wide mode of Sentinel-1 at a medium resolution. So this dataset will provide images with radiospectral and square pixel without phase transformation. So in that way, it is suitable for clear medium resolution surface observation. And that's what we're going to use to visualize simply the iceberg. So for seawater current data, we are going to use Copernicus Marine Service product, which is referred to here. So it's the global total Ekman and geostrophic currents and at the surface and at 15 meters depth. So as the title indicates, we have current data at two different depth levels, so 0 meters surface and 15 meters, and includes both the geostrophic current and Ekman current components calculated using ERA5 data. So for this dataset, we will retrieve the eastward and northward velocity fields, which will allow us to also calculate the total current speed. This dataset is generated by combining satellite observations and by combining several satellite observations. And then for the wind data, we are also going to use the Copernicus Marine Service product, which is the global ocean monthly mean sea surface wind and stress from scatterometer and model. So as indicates, we will use monthly wind data. So it combines several sources, ERA5 analysis data, so from models, and also satellite scatterometers observations. Same as with current data, we are going to retrieve the eastward and northward components of the wind field. So in this table, you have a summary of the different datasets that we're going to retrieve using the WEkEO platform. So for each of them, you can visit the dedicated WEkEO pages, and from there you can access even the source page of the product, which contains, for instance, here a user manual, create information documents. So if you want to dive deeper in the analysis of those products, well, you have plenty of information easily accessible. And you can see here on our on the temporal coverage that it will cover the calving event of the A76 iceberg, because as you remember, it was in May 2021, and those dates are covered by those datasets. And additionally, we are going to use iceberg tracking data. So this is not available on WEkEO, but it is retrieved from the US National Ice Center. It monitors several icebergs in the South Pole. So you can see on the website we have several indicators of icebergs, and a lot of archive data that you can download. So feel free to visit this page if you need to. So in our case, we've already pre-downloaded some data here from this website. Okay, so now that I've presented to you the products that we're going to use, here is how to retrieve them. So I'm going to show you two ways of retrieving data on the WEkEO Jupyter Hub. So first of all is the traditional HDA API. HDA stands for Harmonized Data Access, and it should work with most WEkEO datasets. So if you need to know more about this particular data access API, there is a dedicated article here, so feel free to visit it. In this notebook, I'm just going to quickly use it. So first of all, you need to set up this file, .hdrc, in your home directory on Jupyter Hub, which should contain your username and password for the WEkEO website. So you can just execute this cell. If you don't already have this file, you just ask you your credentials, and then the file will be written in your home directory. And now we are ready to use it, this API. So what you should do is when you want to use it, you should use a data request file, such as this one here. This is a data request for one of the Sentinel-1 image products, and it looks like this. So basically here I have the dataset ID, which is Sentinel-1. Here is the product identifier that I want to retrieve, and those are generated automatically. I didn't really set them myself. I will show you why. So in order to know what to write in your data requests, what you should do is go to the WEkEO Data Explorer. So this is the WEkEO data viewer that you may already be familiar with. So select the dataset that you want to download. And for example, here on water velocity, you can just enter the different parameters that you want on the download menu. Here, 2 depth levels, etc. And then click on this button, Show API Requests. And here you can see that the request is in the format that I've shown to you before. Copy it and paste it on your file. And of course save it. So this is how you set up a data file request. And for instance here I reopen it. And after this request is set up, you can retrieve it on the from the WEkEO website. So here you can see that the Harmonized Data Access client is looking for my dataset, which is here my Sentinel-1 image. You can see that it's found a match, and now we can just download it in the data directory. Alright, just took a few seconds, and you can see in the data directory that we have our Sentinel-1 image here. So this image is from April 2021. You can see it here on the file name. So this is like about a month before the iceberg detached from the ice shelf. So we also have a second image, which is from May 2021. So which was taken shortly after the calving of the iceberg. So the data request is here. And you can see here on the file name that I'm asking for that it is from the 23rd of May, so this is soon after the calving of the iceberg. So I've written this function to download WEkEO data more quickly. So all the steps here are just gathered within one function, opening the data request file, finding the matches, and downloading the data. Same as before, it should go pretty quickly. It's found a match. And it's downloading. Perfect. And if I refresh here, I can see that I have my second image. Then, for the Copernicus Marine Service data, I'm going to show you another way to access the data, which is the EarthKit library. So I've mentioned it before, so I've shown you how to install it on the and make it available in the in this Jupyter environment. So basically, it allows us to retrieve several data sets from the WEkEO platform without having to download the files in the file system like in this case. So basically, it works with the same kind of data request files, so the JSON files that we have here. We have also the currents and the wind request file that I've written. You can take a look at them if you want, with the two depth levels, the start and the end date, and the two variables here. And so if I show you the different steps to use EarthKit, we have the same thing here to read the data request file. And here with EarthKit, we just have to use this from source function. So specify that we want to retrieve data from the WEkEO platform. Here is the ID of the dataset. So you just have to copy paste this identifier here. And the request data file is also specified here. And in the end, you just have to convert the data to an X-array dataset, which is the standard format that we're going to manipulate in the later sections. So I think I had already cached the data, so it worked almost instantly. And for instance, here, if I want to look at my current dataset, it is available here. I have my two depth levels, so 0 and 15 meters, while several latitude and longitude coordinates, and also we have several dates of data. You can see it goes from beginning of 2021 to the end of 2023. All right, so now we're ready to do our case study. So first of all, we're going to use the Sentinel-1 images to visualize the A76 iceberg. So remember, we have one image before the calving and one image after the calving. So first, as you can see here, the images have come in a zip format. So we're going to use this cell to unzip them using the zip file library from Python. And you can see here that we have our two new folders. which contains several directories and data files. But what we want is the measurement, which is the image itself. So let's open them here. So we have the April image and the May image. Let's read them with rasterio and just visualize them and see what the results is. The images are quite large, so it takes a little time to plot. And here is our result. So it's located in the runny ice shelf. So here is the image from April. We can already see that we have a little crack here maybe. And on May, it is clear that we have a totally detached iceberg from the ice shelf, which you can see has the same shape as the image I had shown you in the intro here. But here it was taken at a much later time, so the iceberg has had the time to roam freely in the ocean months after the calving. And this is what we're going to look at now. So of course here is an image right after the calving, but you can find also other Sentinel-1 images later on with the iceberg in other areas more remote from the ice shelf. So feel free to explore the Copernicus data space to find other images that show this iceberg. There are plenty of them. It's very large. It's 170 kilometers long and 25 kilometers wide. So it's one of the largest icebergs that has calved recently. And now we're going to look at its trajectory on a longer time scale. So, as I've mentioned before, we have iceberg tracking data retrieved from the US National Ice Center that we retrieved in this folder. So the data files that are provided by this service include all of the iceberg that are being monitored. So we have to do some pre-processing with pandas in order to be able to retrieve the A76 trajectory. So I'm going to show you what I mean by opening one of the datasets. So here you can see, for example, that I've opened the dataset from 2021 June, from the 4th of June 2021. So this is weekly data. I haven't mentioned that, but this website provides weekly data, and we've only retrieved one dataset per month for the sake of practicity and easy manipulation. And you can see in the iceberg column here of the table that we have the positions of several icebergs here. And for convenience, we only want to retrieve the A76 iceberg. And in that case, we can see that we have 3 A76 icebergs computed in this dataset. Basically, the iceberg A76, as it was very large, was at some point split split in 3 different parts during its life, if we can talk about the life of an iceberg. And A76A is the biggest part of the 3. So this is the part that we're going to monitor in this notebook. And so, as you can see here, we have several dozens of data files covering so from June 2021 to here we can see, the end December 2023. And we are going to open each of these files and retrieve only the A76A iceberg. So this is what we do in this loop here. And so everything here has been saved to this CSV file, A76A tracking.csv. And now if we open it, you can see that this time the only iceberg we have in our dataset is A76A, and you can see here that its latitude and longitudes are evolving with time here. And so we're going to use that to plot the trajectory of the iceberg on a map. So this is what we do here. Well, it's quite simple, as you can see. We just use Matplotlib and Cartopy to plot a map centered on the low latitudes on the center of the South Pole, using the South Pole stereo, so our map will be centered on Antarctica. We add some coastlines, and finally we plot our dataset using the latitude and longitudes that we have seen here. And so you can see here's the departure of our iceberg, and it went northward here, and then at some point it started drifting eastward and went around this little island and still went northward. And now, so we can now clearly see its trajectory. And now we're trying to see if we will try to see if we can find and identify potential drivers for this trajectory using currents and wind data. So let's start with the currents. Here is a reminder of the dataset that we have retrieved using EarthKit. So as you remember, we have two depth levels. We're going to average the dataset over those levels because well, the two levels have an importance because the iceberg, of course, has a big part that is located underwater. So both layers have an influence on the trajectory of the iceberg. So we have the latitude, so we have the field longitude latitudes, and also the different dates here. So we have daily data, as you can see. So if you want to see a sample of the data, you can click on this icon, and here you can click to show the metadata of the dataset to see well, additional information on the variables, their units, for instance. Here you can see that our current field is in meters per second. And here we have our two components and additional metadata information. So as I've mentioned, we have two depth levels, so we are going to average the dataset because the two layers have an influence on the trajectory of the iceberg. Well, should have an influence at least. And in the map below, we're just going to show a random date. So here, for example, the 4th of March 2022, just to take a look at our current field. So you can see here, this is where we average over the depth dimension. You can use the min function over and specify the dimension in which you want to, for which you want to retrieve to average the dataset. Here we prepare the components to draw the vector field of the currents. And here we calculate the total current velocity. And here is what we have as a result. So we have a current field centered around the Antarctic. You can see here that the current goes quite uniformly northward, and it gets a little more chaotic in the higher latitudes. And what we can also see is that our dataset doesn't really cover here the very low latitudes. So this is quite a problem for us because we saw before that the trajectory of the iceberg started around here before going in those higher latitudes. So in order to, well, compare the trajectory to the current field, we will have to use the data only at later dates, probably at least starting from the end of 2021, in order to the iceberg to be within reach of this current field. So this is what we're going to do here. Basically, we will do an animation of the trajectory of the iceberg along with the current field at the same dates. So basically, we are averaging the current data between the date of the trajectory sample and the previous one, in order to have a representative current direction during the movement period of the iceberg. And so basically we draw as many maps as we have, as many maps as a number of positions of the iceberg that we have. We plot the current field and the trajectory of the iceberg, and all those maps are stored in this out data folder and look like this. Here you can see the trajectory of the iceberg and the current field around it. And here, for example, we are in February 2023. And using these libraries, we can animate our results. Sorry. So you can see the dates evolving here and our dataset our iceberg moving in this area. And here, if we look closely, we can see that it follows the current field quite well. Like it is surprisingly, I mean, not necessarily surprisingly, but from what we can see from the animation is there is quite a good consistency between the directions here of the vector field and the trajectory taken by the iceberg. So we'll see that in more details afterwards, but this is quite encouraging. So now let's do the same with the wind data. So same thing here. So this is only surface data, so we don't have any depth dimension. We still have, so this time it's monthly data, as you can see here. And it ends also at the end of 2023. And same thing here, we're going to do the same animation, but this time instead of the currents, we're going to use the wind field. So it takes some time because it has to draw several maps at the same time. Okay, I think it's going to be finished very soon. From this icon C, you can see that the cell is still working, still being executed. At some point, yes. So it's finished. And now we just have to compute the animated image and display it. And we can see on the vector field from the wind that, well, it has quite a homogeneous direction. It goes mostly eastward during the whole period in this area. And, well, our iceberg is also mostly going eastward, so this is also quite consistent. Maybe the wind is, well, a driving factor, perhaps not as much as current, but yeah, from what we can see, it's quite consistent. And now, to have a more precise view, we're going to plot the successive directions of the currents, the wind, and the iceberg movement. So to do this, we are going, in order to plot the successive directions, several steps are needed. First, for the iceberg, we have to compute its direction at each time step. And so to do that, we're simply going to use the coordinates of the start and end date of the time of the time step and use trigonometry to derive the eastward and northward components. And same thing, we're going to determine the general direction of the currents and the winds. We already have the eastward and northward components, so it's easier. And this time we're going to average the eastward and northward components, so over the rectangle defined by the start and end point of the starting and end positions of the iceberg for each time step. For example, in here we're going to average, for this time step here, we're going to average the direction of the wind in this rectangle. So it will give us the general direction that might have for the iceberg in this area. And finally, just for the plotting readability, we're going to normalize all the vectors so that all the arrows have the same length regardless of the actual intensity of the wind or of the currents, or the velocity of the iceberg. So this is what is done. It is quite a big cell. It looks big, but it's actually not too complicated. It's just because we're processing 3 datasets at once. You can see here that we set up a geode variable using the PyProsh projection. Basically, we're just using a model of the ellipsoid of the Earth in order to calculate the vertical and the eastward and northward components of the trajectory of the iceberg. This is done here. Because we have to convert the coordinates to actual distances. So this is why we need a model of the Earth. And that way we can retrieve the 2 components. We can do easily the same thing, so as I've mentioned, by averaging over the different rectangles, so the components for the currents and the winds. And finally, we normalize all those components in order to have arrows of the same length in the plot. So let's just draw this map, no, not a map, so the resulting graph. So in blue we have the successive directions of the iceberg. In orange we have the successive direction of the currents, and in green we have the successive direction of the wind. So here you can see the different dates here. So we start in June 2022, we end in October 2023. And you can see here that the arrows of the iceberg and the currents are often going quite in the same direction. We have a more of a northward components here for the iceberg, but also eastward, and the currents kind of follow the variations of the iceberg direction. So we can derive from this that the currents are quite a strong driver for the iceberg movement, and also the wind goes eastward most of the time, just like the iceberg. So we can make the hypothesis that the wind also have a small influence, but well, goes quite in the same direction, except at a few dates here. But here this time we can see that the currents also have quite a strong influence here, so the correlation is visually quite strong. But of course we have some discrepancies, which is expected, because of course there are other factors that are more difficult to identify and to follow. First of all, we don't have any information of the bathymetry, the local bathymetry. So the bathymetry is the underwater elevation of the ground, which of course has an influence of tides, and also of course on the trajectory on the iceberg. We don't know if the iceberg encountered any obstacles during its travel, and of course there are some other factors that are even more difficult to identify. Even the mass itself of the iceberg can influence its trajectory due to inertia. So those are some things that we don't have any data on, and that might also have an influence. They explain the few discrepancies that we can observe in this graph. So we're reaching the end of the tutorial. You can see that in this notebook we've explored the drift of the A76 iceberg. So we visualized it with Sentinel-1 images. We analyzed the actual tracking data provided by the US National Ice Center, and we demonstrated that there were quite significant correlations between especially the trajectory and the currents in that area, but also the wind showed quite good agreement with the tracking data. And if you want to go further in this on this topic with this notebook, here are a few exercises. So if with a different set of difficulties, levels of difficulty. So for example, in section 6.1 we plotted the current field on a random date, so you can always explore the current field by yourself by plotting at other dates. Also, I've mentioned it before, but you can find other Sentinel images and try to follow the iceberg trajectory using satellite images. So you should have to find several images at other locations and other dates, of course. It might not be very easy to do with WEkEO, but you can use the dataspace browser to retrieve the image endfire that you want. So I recommend using the Copernicus browser in order to find images, because it's very responsive and intuitive. And also this notebook, so we was dedicated to the so here is the Copernicus image. You should have to create an account to visit it, but it's up to you. This notebook so is dedicated to the A76A iceberg. So this is what we had observed in our tracking dataset. But you can also reproduce this analysis following any of the icebergs that we may have seen here during our investigation of the tracking datasets. So the point is, you can look at other trajectories and replay and do the same analysis with the current and the wind data, and see if for those other icebergs, well, currents and winds are also well correlated or not with their movement. Okay, so we're reaching the end of this tutorial. I hope that you have enjoyed this training, and if you have any questions, feel free to contact the user support of WEkEO. This is the end of this notebook, and I hope you had a good time, and thank you very much for your attention. Goodbye.